Let us continue the next question. Question number 31. With the following highly basic hydroxide, all the lanthanide hydroxides are given. While discussing about the lanthanide contraction effect, I said from left to right that ionic and atomic sizes are decreasing. Then for lanthanides from left to right, the basicities of oxides and hydroxides gradually decreasing. As the ionic size is decreasing, the basicities of oxides and hydroxides gradually decreasing. Now you see the options. Option A is actually lanthanum hydroxide is given. Lanthanum is actually very big. Lanthanum hydroxide is given, LaOH taken thrice. Second option, praseodymium, PrOH taken thrice. Next, neodymium, NaOH taken thrice. Thus one, lutetium hydroxide. Among these particular, lanthanum is very big in size. Yes, lanthanum is big in size. Therefore, lanthanum to OH bond length is very high. Come to the lutetium is smaller in size. Lutetium to OH bond length is high. Then, whichever is having greater the bond length, the bond energy is less, easily dissociates, easily ionizes. This is what coming to be plus and minus. So, among these particular hydroxides, this particular lanthanum hydroxide, lanthanum is very big in size. Lanthanum to hydroxide, bond length is very high. Therefore, easily ionizable is what? Lanthanum hydroxide, producing more number of OH minus ions. Therefore, answer A is the correct here for 31. A answer is what? A for this particular question. Question number 32. Which of the following produce heavily hydrated ion? So, from according to lanthanide contraction effect, lanthanum to lutetium, the ionic size is decreasing. Among the given, this particular options, first option is given as lanthanum plus 3, second option cerium, third option praseodymium, fourth option lutetium plus 3. Among these three, you can understand lutetium plus is what? Very small in size, lanthanum is not big in size. Because the ionic size, the charge density is very thin. So hardly it can accommodate only one layer of water molecules. Hardly 6 or 8 water molecules can be accommodated by this particular lanthanum plus 3. Come to the last option. The fourth option is C, lutetium. Lutetium is what? Very small in size. Then it is having greater charge density. Plus 3 charge density is very high for this particular. You know well, any ion which is having smaller size, greater charge density, it can accommodate more number of water molecules through strong electrostatic force. Look here, lutetium plus 3 can accommodate not only one layer of water molecule, first layer, second layer, third layer of water molecules, it can accommodate. So 3 layers of water molecules it is accommodating, more number of water molecules can be accommodated by lutetium plus 3. Therefore, lutetium plus is what? Heavily hydrated. So this particular 32, question number 32, that answer is what? D. Question number 33, the number of unpaired electrons in ytterbium plus 2, europium plus 2 is. See option A, it is given as what? 27. Option B, 70. Option C, 74. Option D, it is none. Ytterbium plus 2. Ytterbium plus 2 electronic configuration is what? F14, D0 and S0. D0 and S0 is the electronic configuration ytterbium plus 2. And coming to next one, ytterbium plus 2, then europium plus 2. Europium plus 2 is what? It is F7, D0 and S0. D0, S0. Now we consider in the case of ytterbium plus 2, here there is no unpaired electron, and in the case of the 7 unpaired electron, the answer should be what is the 0 and 7 should be there. 0, 7, but options are not given. 0, 7, 7, 0 is given. Therefore, here answer D, the correct one, answer D for this particular 33 question number. Coming to question number 34. Separation of lanthanides and ion exchange method is based on. See, option A is given as size of unhydrated ions. Option B is given as basicity of hydroxides. Option C is given as size of hydrated ions. Option D is given as solubility of their nitrates. Solubility of their nitrates. So among this particular option B, you see B is basicity of hydroxides, nowhere related to separation of lanthanides, and size of unhydrated ion, nowhere related to this particular. Ion exchange method is based on only sizes of hydrated ions. A bigger hydrated ion, consider lutetium plus 3 ion, which is heavily hydrated. A bigger hydrated ion is not actually sticking into the ion exchange resin, ion exchanger. Therefore, whichever the bigger in size, lutetium plus 3 heavily hydrated, this is what first eluted, which cannot fix into the interatomic spaces, intermolecular spaces in the resin. Therefore, whichever the bigger hydrated ion, that is eluted first. So according to this particular separation of lanthanide ion, based on what factor? The separation of lanthanide ions by ion exchange method is based on sizes of hydrated ions. A bigger hydrated ion is eluted first, followed by smaller and smallest. Therefore, option C is the correct answer here. So answer is what? C. Question number 35. Which pair of compounds is expected to show similar color in aqueous medium? Option A is given as what? FeCl3 and ZnCl2. Option B is VOCl2 and cupric chloride. Option C is VOCl2 and ZnCl2. Option D is ZnCl2, MnCl2. Whenever a color of a particular pair of compounds is given, check it which pair is having same number of 100 electrons. Generally, same number of 100 electrons are there, that particular pair can be expected to exhibit same color. Coming to the option B here, VOCl2, vanadium oxidation number coming to be plus 4, and CuCl2 means what? Copper again plus 2. This particular vanadium plus 4 means only D1 electronic configuration, 1 unpaired electron is there. Coming to copper plus 2 means D9, this is carrying 1 unpaired electron, this is also carrying 1 unpaired electron. Therefore, this pair can exhibit more or less identical color. Therefore, question number 35, the answer is B. Coming to question number 36, acidified solution of potassium dichromate when treated with a solution of iron peroxide forms a blue solution that is subsequently turns into green on standing. The oxidation states of chromium in the blue and the green solutions are respectively. A very important question, repeatedly, frequently this particular question is coming. Potassium dichromate on reaction with the hydrogen peroxide producing a compound first, that is blue in color. Then again this you are actually keeping the solution like that only. This particular blue colored solution decomposes and again converts into what? A green colored solution. What is the reaction actually taking place in this? Option A is given as, what are the oxidation states of this? I will show the equation and I will explain to you. Option A is what? Plus 6 and plus 6. Option B is what? Plus 3 and plus 3. Option C is plus 3 and plus 6. Option D is plus 6 and plus 3. These are the options given. First, let us check what is the reaction between potassium dichromate and hydrogen peroxide. Then what is happening subsequently to this particular product produced. C. K2Cr2O7 acidified H2SO4 and hydrogen peroxide. This is the reaction. This particular reaction is carried out in ether solution, ether solvent. See the products what you are getting here. This will be giving rise to 2CrO5 chromium peroxide you are getting. Chromium peroxide plus chromium peroxide, and you are getting K2SO4, and check it how many water molecules, 5H2O. This is the reaction. This particular chromium peroxide, this is actually blue in color. Blue, this is serine only, ether solvent. Ether solvent only we are looking this particular serine ether solvent, blue color. This is what chromium peroxide. Read the name also, chromium peroxide. Chromium peroxide. Blue in color, chromium peroxide, seen in this particular ether solvent. The oxidation number of chromium peroxide is +6. So first compound oxidation number +6. This subsequently, this whenever you are actually allowing to stand for few minutes, it is most unstable compound. Why unstable compound? It is a peroxy compound. See this particular compound, butterfly structure, you might be knowing this. The structure of this particular compound is butterfly structure we call. This is the structure of the compound. The chromium in this is what? +6. It is a diperoxy compound. It is a peroxy compound, unstable. If you are allowing to stand for few minutes, slowly it decomposes in the presence of again same acid. How it is decomposing? See, this is what CrO5 plus again sulfuric acid. In presence of sulfuric acid, it is what 6. You take 2 CrO5 and 6 H2SO4. Then ultimately you are getting a compound Cr2SO4 taken thrice. This 3 Cr2SO4 taken thrice. This you take 4 times to balance it. 4 CrO5, 6 H2SO4, 2 Cr2SO4 taken thrice, plus you are getting 6 H2O plus 7 O2 you are getting. This particular compound is chromic sulfate. This is green in color. This is green in color. See, first a compound you are getting blue. On standing, since it is less stable compound, it is converting into another compound, is chromic sulfate. Blue colored solution after some time turns to green color. But the oxidation number of this +6. But the oxidation number of this chromic sulfate, Cr2SO4 taken thrice, the oxidation number of this is what? +3. So answer D for this particular question number 36. Answer D. This is what D the answer for this particular question. It's very important, and remember this particular balanced equations, how you are getting this particular chromium peroxide and again chromic sulfate. This is blue in color, this is green in color. Right. Coming to question number 37. Arrange the cerium +3, lanthanum +3, promethium +3 and ytterbium +3, increasing order of the ionic radii. What are given? C, cerium +3, lanthanum +3, promethium +3 and ytterbium +3. These are the ions given, and we have to arrange these particular according to their increasing order of ionic radii given. You know, according to lanthanide contraction, the lanthanides left to right, the ionic size is decreasing. Ionic size is decreasing. Now you see, whichever actually right hand side, they are having got smaller ionic size, left hand side they are having got a bigger atomic size. Therefore, which is actually right hand side, let us consider ytterbium +3 smaller in size, then followed by promethium +3, followed by cerium +3 you take, followed by this particular lanthanum +3. This should be the answer. Coming to options, which is the correct option? You see, ytterbium +3, promethium +3, cerium +3 and lanthanum +3. For this particular question 37, that answer A is correct. So answer is what? A. Coming to question number 38. Question number 38. Cerium 58 is an important member of the lanthanoids. Which of the following statements about cerium is incorrect? Now, option A is a common oxygen state of cerium is +3 and +4. Yes, cerium exhibits +3 and +4 commonly. We agree plus 4 is more stable, but both the oxidation states exhibited by cerium plus cerium metal. Coming to option B, cerium plus 4 acts as oxidizing agent. Yes, cerium plus 4 acts as oxidizing agent because cerium plus 4 is actually tendency to take electron, therefore it acts as oxidizing agent, because in comparison to plus 4 oxidation state, often it is exhibiting plus 3 also, therefore it is having the tendency to take electron. Yes, acts as oxidizing agent. Coming to option C, the plus 4 oxidation state of cerium is not known in solution. Remember, cerium plus 4 is only stable in the solid state. Whenever cerium plus 4 salt put into aqueous solution, it is easily converts into plus 3. In aqueous solutions, cerium plus 3 is more stable. Therefore, cerium plus 4 oxidation state, cerium is not known in solution here taken. No, not known in solution. Whenever you take this particular cerium plus 4, you are putting into water. Cerium plus 4 is actually given water. Which of the following is the incorrect statement? This plus 4 oxidation state of cerium is not known in solution. Whenever a plus 4 salt put into a aqueous solution, plus 4 easily converts into plus 3. Therefore, plus 4 is not well known in aqueous solution for cerium. So, here the option C is the correct. So, answer C. Coming to question number 39. Lanthanide contraction is caused due to A. Appreciable shielding on outer electrons by 4f electrons from the nuclear charge. Second option, the appreciable shielding on outer electrons by 5d electrons from the nuclear charge, and the same effective nuclear charge from cerium to lutetium, and the imperfect shielding of outer electrons by 4f electrons from the nuclear charge. Generally, lanthanide contraction we talk about. Two factors you have to take in the lanthanide contraction. One is 1, 2, 3, 4, 5, 6 you take, 6 shells. Lanthanides appear from 6th period, therefore 6 shells are written. What is the actual concept about this particular lanthanide contraction? This is due to entry of differentiating electrons into 4f orbitals of antipenultimate shell, inner shell they are entering, first point. Second point, due to increase in the nuclear charge by 14 units, see 14 electrons are entering, 14 units of nuclear charge increasing, first point. Second point, what you say, in addition to all these, 4f orbitals are poor shielders. Therefore, nuclear charge is directly working on this outermost orbital electrons we see. Because of this particular reason, this particular outermost orbital electrons are dragged towards the nucleus, attracted towards the nucleus. This is the reason for lanthanide contraction. So, coming to this particular option D, the imperfect shielding of outer electrons by 4f electrons from the nuclear charge. This is the correct option. This 4f orbitals are poor shielders, therefore outer orbital electrons are dragged or attracted toward the nucleus, therefore gradually atoms are contracting. So, here the answer D, we take the correct answer for question number 39, answer is what? D. Coming to question number 40. See, the actinides exhibit more number of oxidation states in general than the lanthanides. This is because, so see, in comparison to lanthanides, actinides exhibit variable oxidation states. Option A is given as the 5f orbitals are more buried than the 4f orbitals. He is saying 5f orbitals are deeply seated. Coming to the second one, there is similarity between 4f and 5f orbitals in the angular part of wave function. That is also not the correct answer for this. Coming to the actinides are more reactive than the lanthanides, and the D option is given as 5f orbitals extend further from the nucleus than the 4f orbitals. So, option D you can consider the 5f orbitals are actually extending more. 5f orbitals are extending more from the nucleus in comparison to 4f orbital. From the nucleus more extending from the nucleus. This is the reason for why these actinides are exhibiting variable oxidation states. Or you consider in comparison to this particular lanthanides, the energy difference between 5f and 6d, 5f and 6d you take. The energy difference between 5f and 6d orbitals is less. 6d orbitals is less. Therefore, electrons easily from s orbitals, d orbitals, f orbitals can be easily involving in the reactions. Therefore, electrons from s, d and f, all the three orbitals easily participating in chemical reactions. Therefore, the actinides are exhibiting more number of oxidation states in comparison to lanthanides. In general, we say actinides exhibit variable oxidation states, but lanthanides cannot exhibit variable oxidation state. This is the reason any difference between 5f and 6d you take, or 5f orbitals are more extended from the nucleus than in comparison to 4f orbitals. Here, option D is the correct. Coming to question number 41. Question number 41. Larger number of oxidation states are exhibited by actinides than those by the lanthanides. The main reason being A. Option A. 4f orbitals are more diffused than 5f orbitals. B. Lesser energy difference between 5f and 6d between 4f and 5d orbitals. More energy difference between 5f and 6d than between 4f and 5d orbitals, and more reactive nature of actinides than lanthanides. So answers are, these are the answers. What I discussed, the energy difference between, come to the lanthanides and actinides. In the case of actinides, the energy difference between the 5f orbitals and 6d orbitals is less. Therefore, electrons are easily involving from d orbitals and f orbitals in the case of actinides. See, come to the option B there, lesser energy difference between 5f and 6d. Just now I given here the energy difference between 5f and 6d orbitals in lanthanides is less. Therefore, electrons from s orbitals, d orbitals and f orbital. From 3 orbitals easily electrons are entering into chemical reactions. Therefore, these actinides are exhibiting more number of oxidation states. Say, actinides are exhibiting easily variable oxidation states than lanthanides. So, here the answer B is the correct for this particular question number 41. Coming to next question number 42. Question number 42. In context with the transition elements, which of the following statements is incorrect? About transition element, which of the following is incorrect is asking. Coming to the question number, that option number 1, A you take. In addition to normal oxidation states, the zero oxidation state is also shown by these elements in complexes. Yes, in most of the D block elements, they are exhibiting different types of oxidation states and also exhibiting zero oxidation state. You take simple example, nickel tetracarbonyl. No, carbonyl is neutral ligand is well known. This in this particular what nickel is 0. Yes, that is correct. Coming to option B, in the highest oxidation state, the transition metals show basic character and form cationic complexes. So what is said, in the highest oxidation number, transition metals are showing basic character. That is wrong. I given while discussion of this particular transition metals, a metal with different oxidation states whenever is given, choose the metal ion with lower oxidation state, that is more basic I said. The metal ion with higher oxidation state, that what I said acidic. But what is given in this option B, in the highest oxidation state, the transition metal is showing basic character, not basic character. In the highest oxidation state, they are showing acidic character. So, option B is incorrect here. Coming to the option C also, in the highest oxidation states of first 5 transition elements, all the 4s and 3d electrons are used for bonding. See, a D element, a D block element is actually exhibiting highest oxidation state. It is losing all the electrons from s orbital and d orbital. Consider manganese for example. Manganese you take. Manganese is exhibiting maximum oxidation state of +7. How it is exhibiting? Yes, it is losing electrons from d5 and s2. All the 7 electrons it has to lose, then it is exhibiting. Correct only. The maximum oxidation state for a D block metal is only possible when it is losing electrons from the d orbital electrons and s orbital electrons. So option C is correct here. Coming to the option 4, once the d5 configuration is exceeded, the tendency to involve all the 3d electrons in bonding decreases. Once d5 electronic configuration is exceeded, then first half and second half you take. The nuclear charge will be gradually increasing. Therefore, after d5 configuration, the nuclear attraction over the d orbital electrons increases. Therefore, losing of electrons whenever d5 electronic config exceeding d6, d7, d8 like that, they cannot easily lose the electrons as they are losing electrons up to d5 configuration. Therefore, here option B, so highest oxidation state of the transition metals show basic character. That is wrong. They are showing acidic character. So, here answer B is the correct.